So first of all, what is Apache Pulsar? Well, Apache Pulsar is essentially like a next-gen messaging solution that was built for cloud-native environments, right? It is, to an extent, very similar to Apache Kafka, which is very popular these days. I'm sure you guys heard about it, and if not, I mean, go ahead and check it out. But essentially, the way it works in way similar to Kafka, or the main basic idea is that you produce messages and then you can have consumers which process these messages, right? And this can lend itself to like many use cases, including event-driven applications. Now, why am I talking about Pulsar in particular as opposed to Apache Kafka? Well, first of all, because it's a little bit newer, so you folks probably didn't hear too many things about it. It wouldn't be as interesting as if I was talking about something intimately. And on the other hand, the reason why I'm talking about Pulsar is because I had the chance of using it recently for a use case where Kafka really didn't, I don't know, deliver for me, and I wanted to explain the reasons why I liked it more, right? So long story short, Apache Pulsar does a couple of things better, and I'm going to show it in the code in a minute. And in particular, it has a more flexible broker approach, and this allows you to basically like handle partitions in an easier way as opposed to Apache Kafka. So let's dig into it. I'm going to show some code. So here is a very boilerplate kind of like Gradle project. I mean, I'm basically like later on you can find the URL for the GitHub repository with all the code there. So I'm not going to go too much into it. But for people to understand it, basically I'm using Gradle as a package manager. And I'm using JUnit essentially for testing, right? So I'm going to try to work line by line and then run some tests. So first of all, I'm instructing JUnit not to create a new instance of this class for each test function, which seems to be the behavior in general. And this is quite inconvenient because when you use test containers like I'm doing here, line 33, this would basically create new containers for each function, which take forever. And as I was saying, like I use test containers to spin up Pulsar locally using Docker, right? So I'm running Docker. This is my personal laptop for personal usage, so not breaching any commercial agreements. And long story short, as part of the test, I start Pulsar up, and after all the tests run, I stop it, right? So this gives me a clean slate. It doesn't even take too long to boot it, so I'll show you later. And before we got into, the weeds of what the tests do, I'm using some Kotlin functions and functionality basically like make running this kind of test really easy. So one is, I'm sure you understand it, or you're all Kotlin experts, but long story short, by using by lazy, this delegate here, what I'm making sure is I can initialize this variable without making it mutable, and it will only be initialized lazy when I use it. So what's going to happen here is so if I start basically Pulsar container before using this Pulsar client is going to be initialized to target the address of the Pulsar container running locally, and it's going to happen atomically in one go, right? So it's quite convenient in general. Otherwise, I should have declared it like as a late init var and then like initialize it after the Pulsar container would come up. Because before you start the Pulsar container, there is no address because of how Docker networking works, and so basically you wouldn't be able to connect to it. So these debug probes here, so basically what this does, if you haven't checked it out already, you might want to look it up, but essentially it gives you much better visibility of what's going on in terms of coroutines, if anything goes wrong, or at the end of each test. So it's like if it was a thread dump in terms of like, it will basically like log the state of all coroutines, if they're suspended or not, and so on. So let's get into it. So this one is a really basic test, that I'm showing in terms of functionality. I'm going to walk you through it in a minute. But what I wanted to do is I wanted to show you how it would look if I were to just use the standard Pulsar Java client, okay, without making it nicer with Kotlin. And this is still a Kotlin file, so, in Java would look arguably worse. But to give you a good idea. So here what I'm trying to do is I'm saying, okay, run a test, which gives me like a coroutine scope, which I can use for coroutines. So the main idea behind coroutines, I'm sure you guys all know about it, but is that I can do operations that are non-blocking in a way where it actually looks like it is blocking. So as an example, if you consider this line 60, where I'm waiting for the create async operation on the producer, what's happening is here the coroutines will actually suspend and resume after this function returns, right? So it's very different compared to how normally it would look if you were to block the thread. And this allows to basically use the resources on your machine in a more efficient way. Now, all of this is probably going to change a little bit with the introduction of Loom, which is actually now available under, you need to enable it with experimental flags. But essentially, coroutines also do more where they make it simple to basically spin up multiple parallel threads of execution and I wait until they're done. Basically, the main difference between Loom and coroutines is not like these are just completely different implementation. One will replace the other, but it's mostly like for coroutines, what they enable is for you to do stackful based reasoning with multi-threading. So the main idea is that if you spin up a thread, whether it's in Loom or not in Loom from another thread, the parent thread doesn't have like an idea of the child thread, right? And so some operations are in things that is slower or more annoying. So as an example, if you need to close resources, it's much easier to do with coroutines as opposed to threads, whether you use Loom or not. So that said, the run test, that it makes it possible to basically run coroutines without this test function. And here what I'm going to do is I want to send messages as strings. So I'm using this string schema from Apache Pulsar. And I'm going to create a topic, right? So topics in Pulsar can essentially be either persistent or non-persistent. The difference is that if a topic is persistent, even if there are no consumers, the message is going to be appended to the distributed ledger. I'll talk more about this later. While if a topic is non-persistent, then if no consumers are there, the message is going to be discarded. Right? And also that's like state persistence on the broker itself. So here what I'm going to do is I'm going to basically like ensure that the topic works. This is the one exception, as in it's not part of the standard Pulsar Java client, is a function I created. But essentially like creates the topic and it creates the schema, it registers the topic under a tenant and a namespace. This is another key difference between Kafka and Pulsar. So Pulsar is tenant aware because like it has multi-tenancy built in. So essentially what you can do if you're in a B2B2B kind of context is you can model different tenants within your Pulsar cluster, and you can basically have settings that are per tenant. So as an example, things like you could encrypt the storage of messages with keys that are per tenant, and you can create the same the same topic name across different tenants, and Pulsar handles this gracefully because basically this concept has been built in. Okay. As far as I know, last time I checked, Kafka didn't have this out of the box. So here what I'm doing is I'm creating a producer, line 60, and I'm also creating a consumer. And after that, what I'm going to do is I'm going to send a message and wait until it's been sent. And then I'm going to receive it and wait until it's going to be received, acknowledge it, which works in a very similar way that it works with Apache Kafka. And then I'm going to check that the value that I sent in the message is equal to the value that I received. So here, one of the pains of using the Java client directly is that these functions that end with async return a completable future that I need to await every time, right? So for everything I need to do, I need to find the version of the function that uses async at the end, and I need to await it. So why could I not just use this receive function instead, right? Well, it works, but the difference is that this one is going to block the thread, and so it doesn't play well with the coroutine model underneath. So if I run it, unsurprisingly, I mean, it's not much of an output here, but it's going to basically hopefully work. Here is spinning up the Pulsar container. So as you can see, it doesn't take too long. And let's look at how the test will look if I'm using some extension functions that you can create in Kotlin. Now, one of the very nice features that Kotlin has is that if you mix extension functions, you can basically create your own DSL on top of whatever library or SDK a dependency makes available to you, right? So as an example, if I don't want to always like use async functions and then I wait on them, which is already great because, like going back to it a second, these kind of functions that return a completable future are quite handy if you're in a Kotlin context because you can await them and basically bridge the gap between completable futures and coroutines. Now, as an example, is another advantage of using Pulsar, at least in terms of the Java client, because the Java client itself is built to be compatible with Java 8 or more recent. While if you take the Apache Kafka clients in Java, they're compatible with Java 5. And so they basically give you back a future as opposed to a completable future, which is not simple to await in Kotlin. So if you want to use the Java client for Apache Kafka in a non-blocking way using coroutines, it's not as straightforward. Okay. So here, let's go back to it. So what can I do with Kotlin types? Well, essentially what I can do is I can make sure that with my new types, I can remove all these async await kind of behavior. So here, if you see this function, it's a suspending function, which basically means that it plays with the coroutine mechanism natively, right? Now, the other big advantage is I'm using flows here to basically return messages coming from a consumer, like if it was an RX observable or, like a project reactor flow. I don't know if you guys have used flows before, but long story short, yes, it's similar to project reactor flux or RX observable, and it looks like a little bit like a Java stream, so you can do all sort of like map reduce, filter kind of operations, which is a very nice non-blocking or better suspending mechanism in Kotlin, where for each of these functions, you can essentially map a suspending function to it, and it will handle it according to the coroutines mechanism, right? So here, this is going to be like essentially a hot flow. Now, what's the difference here? In Kafka, if you consume from a topic, you're essentially pulling messages, right? So the Kafka consumer is pull-based. It will keep an offset, whether it's in Zookeeper or not, and it will essentially say, hey, give me the next X messages after this offset. Now, in Pulsar, this is all reversed. So essentially, the way the Pulsar broker works is that it will push messages to consumers, and which is great for latency and so on, but at which point some people might ask, hey, but how does it handle back pressure, right? So won't it risk pushing too much and too many messages, which might risk overwhelming the consumer in terms of memory and processing power? And long story short, the way it works is quite straightforward. So when the consumer consumes a certain amount of messages, it renews a maximum amount of messages that the broker can send. So essentially, when I create a consumer, you can specify how many messages the broker can send before receiving a notification of things when processed. And it could be like, I don't know, 500, right? And so if you create a consumer with these 500 messages available, the broker pushes messages until it has either delivered 500 of them or until the consumer will have renewed this quota. And so this is all transparent. If you see the implementation of this flow, it's quite straightforward to basically implement this kind of behavior in Kotlin. And the way you do is you can say you can use the flow builder function here. And what you say is, as long as my coroutine context is active, so this gets canceled very gracefully as well, keep receiving messages and emitting them. Okay. Right. So all good. So I'm going to run it. Once again, nothing extraordinary so far. And you should complete pretty much in the same amount of time. There you have it. Now, you can push this even further, and basically you can make the test more streamlined. Now, one of the features that you can use with JUnit is this idea of inner classes and test interfaces, right? And essentially, if you use interfaces, you can provide default behavior, and that basically allows some sort of like multiple inheritance where you can compose functionality as part of your tests. So here I'm creating a nested class like with JUnit. The main idea is that this test will appear within the nested class context, and I'll show you in a sec what it means. But basically, this is the same test and is even more streamlined. And the way it works is I'm able to call this function like new persistent topic or ensure that it works. And it all looks a lot easier. And the way this works is because this Pulsar test to port is aware of the fact that there's a Pulsar container, a Pulsar client, and a Pulsar admin. And so here, when I say new persistent topic, I can actually, or ensure it works, I can actually access the Pulsar admin client directly, which basically means that I don't need to refer to it here, okay? I'm not necessarily too much of a fan about this approach because it's very concise, but it's also like, it's not necessarily clear what's going on too much. And so basically, but I wanted to show what is possible. Now, another one that it's interesting in Kotlin is this idea of multiple receivers. Now, this is going to look a little bit weird if you've never seen it before. Now, you guys are probably aware of extension functions in Kotlin. So as an example, I could create an extension function on a string called, I don't know, last 3 characters. And this returns another string. And I can say, I don't know, take last 3. If I got another bell to do, right? And what it means is that essentially you could potentially use it like this. So I can say something dot last 3 characters, right? It's almost like this string is in context within this function, right? In particular, it's called a context receiver. Now, what I can do here is I can add multiple context receivers to a function, whether it's an extension function or not, which basically means that this function will only be available if all the receivers are in the context, right? So if you go back to how I'm using this here, I'm saying with producer, which puts this producer, well, of type Kotlin producer as a context receiver. And then within that closure, I'm saying, hey, with consumer, which also adds the Kotlin consumer as a context receiver. And now message dot is the type, basically, this is the actual context receiver for the extension function. And so what's happening is I can call this function because these variables are in scope. Now, for a second, if I were to remove this function is not available anymore because the producer is in the scope, the consumer isn't, right? Which is quite handy. I mean, it's still an experimental function, but I think once this becomes stable, it will definitely have an impact in how people will build things because it's quite handy. Now, this function is arguably not the most convenient, so I don't know if in the future, perhaps the Kotlin folks will want to like facilitate something that looks like this instead. But anyway, so now let's look a little bit at how Pulsar is different compared to Apache Kafka when it comes to partitioning, which is a really big difference. It's also why I personally prefer it. And in Apache Kafka, like if you know how things work a little bit, which is what this test shows, is the main idea is that you create a topic, and for a topic, you create a number of partitions, right? So here, when I'm creating this persistent topic, I'm also like creating a number of partitions equal to 4 on it, okay? And the way Apache Kafka works is that if you have a cluster, each broker is responsible for a number of partitions. And essentially, a partition is a log, right? So when you consume a topic partition, you're basically following a file handle, which implements a log, and this file handle exists within an Apache Kafka broker, which is part of a cluster, okay? Now, this is great because it's fast and logs are really fast to append only, you know, it's all nice, but it has some problems, which I'm going to talk about in a minute. But anyway, so imagine I create these 4 partitions on a topic. Then what I'm going to do, I'm gonna like produce some messages to a topic, and I'm also gonna create a consumer group which has two consumers. Now, this is a very common concept in Kafka, and essentially, like when you join a consumer group with multiple consumers, you will have this behavior where partitions are allocated to each consumer exclusively. So, as an example, if I have two consumers within the same consumer group and I have four partitions, one consumer will exclusively process messages that fall into two of these partitions, and the other consumer will own exclusively and process exclusively all the messages that fall into the other two partitions. Now you might ask yourself why, right? So if I'm just putting messages in a queue, why do I want this kind of behavior? Well, this kind of behavior is actually extremely useful when you want to do in-memory processing, because one of the problems with like, synchronous request or REST microservices is that if you have like, I don't know, an auto-scaling group in Kubernetes with multiple REST microservices, you have no guarantees that updates for the same business entity, I don't know, for the same user, for the same customer, for the same account, whatever it is, you have no guarantees that those updates will reach the same instance. And so the only thing that you can do in order to synchronize and make sure that you don't make mistakes is going to a database, right? So typical REST application, what you do is you say, hey, go to the database with a transaction, do some operation, come back, return the result, right? And so if two parallel operations reach two separate microservices, you will create order in terms of like what goes through by synchronizing, serializing in particular on the database. Now, if you're using Apache Kafka or Apache Pulsar, what tends to happen is if you publish those messages to a partition based on a key, so it could be, I don't know, the account ID or the user ID, and you make sure that all the updates for the same business entity reach the same partition, then you got the guarantee that these updates or events or messages will be consumed by the same consumer. And that allows you to do things like batching and flushing or in-memory processing, which are actually really powerful, and essentially like also makes the application logic much simpler. Okay, so here, if I do this, what I'm saying is, hey, I want to check that the same key doesn't appear across multiple consumers, as we discussed. So each consumer will own two partitions, and each partition will own a number of keys. And also, I want to see that basically across each consumer basically consumes multiple partitions, right? As we discussed exclusively. So I'm going to run it. Cool. So I'm still using Apache Pulsar here, but basically I'm using this subscription type called failover, which makes it behave exactly like Apache Kafka works. Now, what's the difference? Well, the difference is that while in Apache Kafka, this is the only possible behavior, in Pulsar, you can have different behaviors based on what you need, regardless of how many partitions you create. So what am I talking about? Well, what I'm talking about is that, first of all, in Apache Kafka, the minimum number of partitions you can have is one. So a topic is always partitioned, right? So worst case, or best case, depends who you ask, you're only always going to get one partition. While in Pulsar, you can create topics that are not partitioned at all, okay? And the reason why is because basically in Apache Pulsar, you can model different messaging patterns, like as an example, queues with round robin and other patterns that are not really available in Apache Kafka. So what am I doing here? Well, essentially, I'm creating a topic which has no partitions at all. But what I want to do is I still want to have this behavior where each consumer only consumes updates from a specific key. So in here, when I do send test messages, what I do is I use messages that are indexed in terms of key. And so what that means is that if that key repeats itself, you're going to get the same consumer consuming all the messages for the same key, even if we don't partition the topic at all. This is something that in Kafka is not possible. So in particular in Kafka, if you create, say, one partition, within a consumer group, you can only have maximum one consumer which is actively processing. Now in Pulsar, you can have as many as you want because this behavior is decoupled, and I explain in a bit why and how is it possible. Okay. So here what I'm saying once again is I'm creating two consumers within the same consumer group. I'm using this subscription type called key shared, and this will guarantee that all the messages with the same key will be processed exclusively by one consumer or the other using consistent hashing, like if I had two partitions or any number of partitions, but without having any partitions at all. Once again, this is not possible using Apache Kafka. And here you go. Okay. Right, so as an example here, I mean, probably like it's not extremely interesting to look at the terminal, but long story short, what you can see is that for each consumer, there are still no partitions, so the partition index is -1 for all of them because there are no partitions, once again. But then if you look at the keys, the updates for the same key are processed by the same consumer. So as an example here, key is 1 and consumer is 1, and here's the same. Or if I take as an example key is 3, whenever there's going to be another key 3, is going to be the same consumer, okay? Which is really nice behavior. Now, last, the difference is that also the opposite is possible. So in Kafka, once again, if you create two partitions, if you have two consumers, what's going to happen is that they're going to receive all the messages for one partition, one of them, and all the messages for the other partition, the other consumer. Now, in general, this is like a nice idea, but sometimes it's kind of like quite annoying because if you got a lot of consumers and you just want to consume things, you might potentially want to go in a round-robin way, like if it was a queue. So as an example, if you need to dispatch some asynchronous work to complete, this behavior is not always useful, and sometimes it can limit the throughput in terms of what you can achieve, right? So in Pulsar, once again, you can create a topic which has a number of partitions, but you can still decide to consume this topic like if it was a round-robin scenario. Now, the interesting aspect of it is that basically how you want to consume the messages is a decision of the consumer itself as opposed to the producer and the cluster, right? So in Kafka, essentially, when I create a topic, I set the number of partitions, and this sets how the producer behaves and how the broker behaves and the cluster behaves and how the consumer behaves. In Apache Pulsar, this is decoupled. And so essentially the way you store messages on the cluster is decoupled from how you consume them. And this has a lot of benefits, which I'm also going to talk about in a minute. So in this last test, what I'm doing is I'm creating two partitions. I'm telling Pulsar to just consume the messages in a round-robin fashion. And essentially here, what I'm going to do is I'm going to check that the messages, so each consumer receive messages, contain messages across multiple partitions. Now, this is not a guarantee. In general, I could, because, I can't really predict how the round-robin pattern will work, but I'm sending quite a few messages. So this will make it quite likely, right? So it passed. All right, cool. So before we open Q&A, I just wanted to basically mention how this is possible. And essentially, the way Apache Pulsar makes this possible is by using a different storage mechanism as opposed to Apache Kafka. So as I was saying, in an Apache Kafka cluster, once there's a broker, this broker owns a number of topic partitions. And for each of these topic partitions, there's a file handle which models a log. So whenever you, as a producer, publish a message, you decide the partition based on the hash of the key. And essentially, you send this message to a broker using Zookeeper to figure out which broker. And these days, they're working on Raft. But anyway, and then this broker basically appends this message to the file for which it has a file handle open, right? And so when you consume it, you're basically saying, hey, give me the next index within this file handle, the next position. Now, this is quite inconvenient because it has some consequences. So as an example, if I add another broker to the cluster, typically in Kafka, you have to do what is called a partition rebalancing. And what that means is that basically the new broker will have to migrate some data from existing brokers. And in the meantime, things ain't going to work that nicely. Likewise, basically, like if you add multiple consumers into a consumer group, you also have to rebalance how things are going to get consumed. Now, in Apache Pulsar, this is quite different because Apache Pulsar has a different model. So it doesn't use a log model for storage, but it uses like a distributed ledger model. And the way it works is it uses technology called Bookkeeper, which kind of like virtualizes the file system. And how it works is that each broker in Apache Pulsar is stateless, and logically, it is basically responsible for a number of topic partition segments. So the idea is quite straightforward. So if you can imagine like a topic partition, like an append-only log, where you got like the index of the message and the message itself, so you can map it by position. In Kafka, a broker owns the whole long sequence, while in Pulsar, it owns a series of segments within that sequence. So what that means is that the broker ends up being completely stateless. And as an example, you can easily scale up the cluster if you need more processing power, because the brokers are only responsible for brokering and not for storing the data. And so this is also why, as an example, when you add new brokers to an Apache Pulsar cluster, there are no partition rebalancing. And basically, this is much faster and much less inconvenient.